Now we will move towards something a little new, which is a dual vector. You may have seen it in linear algebra, otherwise known as a one form. I will often say one form. Don't worry about where that comes from now. So the dual vector is something you can do abstractly. If you have a vector space V, you can introduce the dual space. I think V star, Sean's notation. Okay, and it's the space of linear maps from V to the real numbers. V to R. So we're going to see what it is more computationally soon, but you should think of it as a little machine, or an element in the dual space, rather. So let's take a dual vector, omega in V star. So how do we think of omega? I like to draw a little picture. That's terrible. This is one of the, I can use this. So I like to draw my little machine here. The machine is omega, and it's got like a little spout. And you send in a vector v. It's got like another little spout. And out comes some number. Okay, and we write that number as omega acting on v. Okay, and it has to be linear, so if you add two vectors in, the sum comes in, then it's omega of the first one plus omega of the second one, and so on. Yes?
Is omega acting on the space V, or like a vector in that space?
Good point. Vector space, capital V. Dual space, capital V. Okay. So then this vector.
Okay, so little v.
Yeah, thank you. That's a huge blunder of mine notationally. That's what I get for not following notes. Makes it more organic, though. All right. Good. Little v and capital V goes in. Little omega and capital V star. What comes out is omega of little v. Okay. And has to have linear dependence on the argument. Okay. Whoa. All right, so if you have a basis, this is all very abstract, but we'll do examples soon. But if you have a basis, and we do, so if you have a basis E hat mu for V, the vector space, then we just say, okay, there's a very natural one. We get a basis theta hat upper mu for V star. You can check, it's a linear algebra thing, that this V star does define a vector space, just because linear maps, basically. And the way you do that is you demand that this abstract vector, E hat mu, it's a vector, so it can get acted on by, actually let's call it, that's okay. That vector E hat mu acted on by our one form, and I have to use another index here, nu. So this thing is going to be delta nu mu. All right, and this is sort of a fancy way of writing the fact that if you had something, x hat, y hat, z hat, t hat, you could introduce something called dx. This is just the notation for another notation. Let's just leave out t for now. Right, and the rule is just, x hat acting on dx. Oh, got them backwards. Yeah. The rule is dx acting on x hat, is 1, but dx acting on y hat is 0, etc. Okay, so it's just a fancy way of saying we make another thing which is just like the simple coordinate basis you're all used to, except it's this basis of dual vectors. Okay? And this notation dx is a very good notation. It agrees exactly with what you've called an infinitesimal displacement like in calculus. And we'll see that in a minute. So this dual vector is the mathematical construction that most nicely maps onto this notion of dx. Okay. Scrolling is the hardest part of my fancy new setup. Okay. So now we can do the same thing. We can say some abstract vector, abstract dual vector, or abstract one form omega can be resolved into its components in a basis and its basis one forms. Or basis dual vectors, if you like. And so this is our abstract one form, this is our basis. Now notice for the up and down indices to work out, I had to put a lower index on the components for the one form, so that distinguishes it from a vector, which has upper index components. But then to get everything to work, I had to put an upper index on the basis one forms as opposed to a lower index on the vector basis elements. Trust me, all this effort is worth it. We're going to really have to pay attention to all this up-down stuff in curved space-time. So just bear with me. And then, of course, we could do it in a different coordinate basis associated with a different Lorentz frame by this same law. And that would be some theta hat mu prime and some omega lower mu prime. Okay? And now the nice thing about using these two bases is we have a really nice formula for the action of a one form on a vector. And let's see that. So let's do that. So we have omega acting on some vector v, and we could resolve that in some basis. So we have omega mu theta hat mu acting on v, I'm going to call it nu. I don't want to reuse mu because I've already used it. I would have problems if I used it again. It would be inconsistent notation. So now v upper nu, and we called our basis vectors e hat lower nu. Now what can we do? Well, our maps are linear, right? That's how we defined one forms. They were linear maps. So I can pull this scalar multiplication and addition through omega mu, right? There's a sum here over nu, so this is really a linear combination. And I can pull it right through omega mu, right through theta hat mu. So I'm going to get omega mu v nu theta hat mu e hat nu. And now I can use my formula up here that you can't see because of this. I'll close that temporarily. Here we go. This formula here is exactly what we need. It tells us, I should have written the brackets for acting on. It tells us exactly what this thing is, omega mu v nu. It's delta mu nu by star. Of course, now I want this back, so by this star equation. Okay, and then, okay. All right, and then, of course, again, our trick with the Kronecker, this just sets mu equals nu. So it's omega mu v mu. So this is a very nice formula, right? Because it tells you how to compute the action of the abstract one form on the abstract vector only using their coordinate components. Yes?
Equation star is just our construction, right?
Yep. It's our construction. We're doing a lot of that today. So it's very nice to use these bases. If you have a basis for the vectors in your flat space, this is the basis you want to use for your vectors in your dual space, because you have this really nice formula where you just add up the components. Yep. I'm not going to have coordinates on my dual space because the coordinates live in the physical space. Then we have this vector space, which is abstract vectors that are in isomorphism with the coordinates, but that vector space doesn't have coordinates. It has vectors. And
It's not like linear combinations, essentially.
what's not like linear combinations?
When you transform the equation above, where you have theta mu of E mu equals delta mu mu.
There's no sum in that equation, yeah. That's defining your new basis theta hat of your dual space. Yeah, I'm just using that. I'm saying that's the best basis to use. It'd be crazy to use any other one, and no one ever does. So you sort of have only one choice of basis. It'd be really weird to have independent freedom to choose your basis in the vector space and the dual space. This restricts it down. Choose your basis in the vector space once and for all. Now you get your basis on the dual space.
Yeah.
And then you can sort of forget about it and just work with components. Yeah?
How do you figure out what omega is?
Well, I could just give it to you. I could list its components, omega mu, and I could say that's the dual vector. Or we'll do an example. The gradient should be regarded as a dual vector, not a vector. And I'll give you a chance to argue about that later when I assert that.
So if you know the components of omega, would you use it then?
Yes, absolutely.
But,
Well, that's where physics comes in. You say, my basis represents this.
okay.
Yeah.
Okay.
Okay, very good. Getting faster at scrolling. Okay, so it's probably time to do the, all right, I'm not going to do the same calculation, but we then demand, this is the same thing we did for vectors, we demand that, omega v could be written as either omega mu v mu, well, it's similar to what we did for vectors, or omega mu prime v mu prime. Well, it's not or, it's literally equal to, right? This thing has to be a good abstract object. So we do this, and you calculate. It's not really worth doing in class. Very similar kinds of calculations. So then using v mu prime equals lambda mu prime mu v mu, which we already knew. That's the transformation law for the vector components. We find omega mu prime equals, and now the lovely thing about this is I can just sort of follow the notation. I need a lower mu prime to match upper mu omega mu. Okay, so I could derive that for you, and it's worth going through it on your own. If you find today a baffling sea of indices, I would absolutely recommend checking this. But you can always remember it by just making the notation work, right? I knew exactly where to put the Lorentz transformation indices, where the prime goes, because I needed a downstairs prime index to line up with the one on the left, and then I needed upstairs to sum over. Okay? So one-form components transform like the inverse Lorentz. Okay, it's basically the same argument about the basis vectors transforming under inverse Lorentz, because we have this sum, and we want that sum to be the same in the two coordinate systems. If the primed components transform like Lorentz, if the upstairs components transform like Lorentz, then the downstairs have to transform like inverse Lorentz, so that Lorentz cancels inverse, and the thing doesn't depend on the frame. Okay? We will use all these formulas a lot in the class, except with general coordinate transformations here.
So is the reason we're I guess I can imagine summation notation effectively takes dot products and
It looks like a dot product with a Euclidean metric, but the actual dot product that we will introduce will be something like this. V dot W is the metric, A to mu nu, V mu, V nu, which is minus W nu, which is minus V0 W0 plus V1
well, I guess
W1.
like
So
H functions in a very similar manner. Right?
only algebraically.
Yeah.
It absolutely involves multiplying two things together and adding them up, but the mathematical and physical interpretation is totally different. This dot product tells you something about lengths, which is provided by the metric, which you add to the structure to know about lengths. This dot product just tells you how this one form acts on this vector.
Well, yeah, I'm more so just referring to generally we are taking. We are.
It's not an inner
We
product.
are doing a sum of components.
Yes, but they're components of a vector and components of a one form.
But like, I mean, we've also done this with two different, or like with just like.
You will never see two vectors written like this. You will never see this.
Well, no, I'm not saying. Like, I'm just like. I guess like before when we had like. When we divided by like, for example, I think T mu we did that before. And
Divided by? No, we've never divided by T mu.
I guess like.
Ask it again when it occurs to you.
Yeah, okay.
So yeah, it's totally fine, but there'll be plenty of opportunities to ask that flavor of question. So let's push forward. Let's not worry about this kind of dot product yet. I think the gradient example will help. But there's one more thing I want to tell you before I do that. So we now have transformation law for vector components, transformation law for vector basis vectors. We have transformation law for one-form components, so we need transformation law for one-form basis vectors for completeness. So again, demand that omega could be written as omega mu theta hat mu, or omega mu prime theta hat mu prime. And then you find the only thing it could be, these thetas have to go like the Lorentz transformation because the omega mu went like the inverse to keep it invariant. So then again, we have this same formula, and here the notation will help you get it right. Mu prime is lambda mu prime mu theta hat mu. Circle that. Okay, and the message there is the one form basis elements transform like Lorentz. Okay, and so the abstract things are invariants, and the different components transform in different ways. Yeah.
What is the inverse Lorentz transformation? And because we're just distinguishing the two by whether or not the mu prime is up.
Yeah, the prime carries a lot of significance.
Are there values different? Like if we write it in matrix form.
One will have V and the other will have minus V. Yeah, they're inverse matrices of each other. Absolutely. Yeah. All right, let's do the example of the gradient, which hopefully will sort of make things a little clearer.